Hello, everyone. Welcome to the first UAA College of Engineering Professional Development Seminar Series this year. The title of today's presentation is Broadband for Rural Alaska, Satellites to the Rescue. I'm honored to introduce our two speakers today, Professor Jens Monk and Professor Alex Hills. Professor Monk is the Department Chair of Electrical Engineering at the UAA College of Engineering. Professor Alex Hills is a Distinguished Service Professor of Engineering and Public Policy at Carnegie Mellon University. At CMU, Professor Hills conceived and built the world's first Wi-Fi network. He worked in the 1970s and 1980s to build public radio stations across Alaska and to develop the state's telecommunication networks so that even small villages could receive television and telephone services. Professor Hills is an inventor with 17 patents. He's a fellow of the IEEE, a member of the Alaska Innovators Hall of Fame, and he has been named Alaska's Engineer of the Year. In 2014, he was awarded an honorary doctorate by the University of Alaska Anchorage. Thank you so much, Professor Monk and Professor Hills, for accepting our invitation today. And the floor is yours.
Okay, thanks, Mohammed, and good morning, everyone. I'd like to start with a vision that some of us had about 30 years ago. Back around 1990, we had this vision of connectivity, and it could have been broadband connectivity, anytime and anywhere on the surface of the Earth. And we thought about a group of satellites orbiting overhead that would provide that connectivity. Now, this graphic was published in IEEE Spectrum back in the 80s. And I thought that even though this artist thought that penguins live at the North Pole, that the graphic still captures the vision pretty well. Well, about 20 years earlier than that, our health aides in Alaska villages had a problem. And their problem was a communication problem. They were trying to communicate with doctors in regional hospitals. In fact, the whole healthcare system in the villages was dependent on health aides in contact with doctors in regional hospitals, and their communication system back then was shortwave radio. Well, shortwave isn't always that reliable, especially when we have the aurora. The aurora is, after all, an electrical storm in the ionosphere, and the ionosphere is the atmospheric layer that's critical for the propagation of shortwave signals. So that was a pretty big problem. The problem was solved during the 1970s with the installation of small satellite earth stations like this one. These were installed in villages all across Alaska. This is a 4.5 meter antenna, so it's about 15 or 16 feet across. That was considered a small earth station back in those days. In fact, we called them small earth stations because they were way smaller than most of the satellite earth stations that were in use back in those days. So it was kind of a technology breakthrough for us to be able to use such small earth stations. And of course, that was what made it economically possible for us to install earth stations in all those villages. So by 1980, those satellite earth stations made possible medical communication in the villages, as I described, telephone service, first one phone in each village, and then later on, a telephone for anyone who wanted one. And there was also a statewide television channel. Now, people who are old enough and remember those days will probably remember the name of that television channel, which was RATNet. It's a pretty memorable name. It's actually an acronym that stood for Rural Alaska Television Network. So the villages had telecom services in 1980, and the services were pretty much adequate by the standards of that day, but then the internet happened. And so if we fast forward to 2021, but even if we fast forward just to the year 2000, many people across the state and across the country were using the internet, and the villages were lagging behind in terms of their access to internet. And now, 20 years after that, it seems like we're all using broadband. We're all using high-speed internet. But the villages not so much. The villages still have a problem with access to broadband. So the technology that we're going to be talking about, low Earth orbiting satellites, we think can be added to the mix that also includes fiber optic cable and other technologies, and that it'll be particularly helpful in rural and remote areas. It's not that low Earth orbiting satellite is a silver bullet that's going to solve all the problems, but we think that it'll be really helpful in Alaska villages. So let's talk a little bit about what we mean by low Earth orbiting satellites. In this slide, we talk about low Earth orbit or LEO satellites and geosynchronous Earth orbit or GEO satellites. The GEO satellites are the ones that we're all familiar with. These are the ones that we've been using for decades now, the ones that we used to help the villages back in the day. And those are satellites that are in orbit over the equator. So they're about 35,000 kilometers up, or if you prefer miles, about 22,300 miles over the equator. And that happens to be the altitude at which a satellite goes around the Earth once every 24 hours. The Earth rotates on its axis once every 24 hours. So that means that a GEO satellite, when seen from the surface of the Earth, stays at the same position in the sky. It looks like it's fixed to someone on the Earth. And that's why when you see satellite Earth stations around, they're all mounted in a fixed position. They don't have to track the satellite because the satellite's staying at the same place in the sky. But LEO satellites are quite different. LEO satellites, they're in much lower orbit, only a few hundred miles up or a few hundred kilometers up, roughly the same as the International Space Station. And that means they go around once every 90 or 100 minutes, something like that. So it's a pretty big difference in a couple of ways. One way it's a big difference is that if you're trying to cover a region of the Earth from a GEO satellite, you can just point a beam down at, say, North America or South America, and that beam can just stay fixed on the coverage area. And you can do all that from one GEO satellite. But with LEO satellites, even to serve a small region, you're going to need a whole constellation of satellites because those satellites are coming around all the time. A satellite will only be overhead or within view for about 8 to 10 minutes before it disappears. And then you need another satellite to come up above the horizon and continue the connection for you. So that's the difference between a GEO satellite and a LEO satellite. So just to summarize, the GEO satellites are in high orbit, 35,000 kilometers up, and that means that they have what we call high latency or high delay, because the satellites are so high, they're so far away, that radio signals traveling at the speed of light take pretty close to a quarter of a second to go up to the satellite and then come back down to another point on the Earth. Now, again, old timers will probably remember talking over telephone connections that are running through satellite. We became very familiar with that living out in rural Alaska. In fact, village to village calls back in those days had to go through more than one satellite hop. So from the time you asked a question until your friend came back with an answer, it took a while and it was really noticeable. Nowadays, you can still notice that satellite delay when you watch TV news and you listen to a TV anchor person ask a question of a reporter in a far off place. And then from the time the question is asked until the answer starts to come back, takes a while and it's noticeable. And once again, those signals may be going through multiple satellite hops. And so that makes the delay really noticeable. I already mentioned that GEO satellites are used for fixed service, but not only is the Earth station fixed, but the Earth station is not moving because with such weak signals coming from so far away, it's not possible to build at least in the current technology, it's not possible to build a station that you could carry around in a handheld device. And so that's what I mean by GEO satellites being used for fixed service to a fixed position at a building or wherever it might be. And GEO satellites do very well in covering low and mid latitudes because the satellites are over the equator. But when you get up to high latitudes, like in the Arctic, things become more challenging. LEO satellites, on the other hand, are in low orbit, and we're going to use just a round number in part of our presentation of 1,000 kilometers, so altitude of 1,000 kilometers, which is kind of in the middle of the range that is used for LEO satellites. That's 600 miles. So those satellites are a lot closer to the Earth, so we don't have that long delay problem, and we get latencies in the range of between about 20 and 50 milliseconds. And then, as I said, it takes many satellites to provide complete coverage. And those LEO satellites, depending on the details of the orbit, may be capable of covering the entire Earth all the way to the poles. We'll talk a little bit more about that in just a minute. But as an example of a low Earth orbit satellite system, I'm going to use IRIDIUM. Now, IRIDIUM is not a broadband system. And full disclosure, I'm on the Polar Advisory Board of IRIDIUM. But IRIDIUM really is not a player in the context of this conversation for broadband, but it is a LEO system. And it's a LEO system that's been around for about 20 years. So I'm just using it here as an example of satellites that are in LEO orbit. And in this case, the orbit is that goes from South Pole to North Pole and back again. Okay, these satellites are about 700 miles up, and this South Pole to North Pole, this is what we call a polar orbit, So this is not only a LEO orbit, but it's also a polar orbit. And I have an animation here that shows those LEO satellites, the IRIDIUM satellites, in their polar orbit. You can see how those orbits work. One thing that's very interesting here is that the Earth is rotating under those satellites. So if you were on the Earth, you would see the satellite maybe rise above the southeast horizon and set below the northwest horizon, something like that. But the circles show the coverage areas of the satellites, and you can see that they're overlapping. And so in this system, every point on the Earth is covered. There are 66 of those satellites in operation. And so if you take the combination of a LEO constellation, like the IRIDIUM one, but make it capable of broadband, now you have a system that can potentially provide broadband service anywhere in the world. And there are two such constellations that are already flying. You may have read about these in the news. One is STARLINK, and the other one is OneWeb. Both of those companies have satellites up there. They are either already providing service or will soon provide service. And that's where we think there's some considerable potential for Alaska. So those are the three LEO systems that we have right now in operation. IRIDIUM actually has a total of 75 satellites, 66 in operation, and there are also 9 spares that are in orbit. That one only provides mobile and portable service. But you know, if you have a satellite phone, if you go out fishing or hunting, and if you use a satellite phone, there's a strong chance that your calls are going through IRIDIUM. And if you have a Garmin inReach device for your wilderness expeditions, Garmin inReach devices, you'll definitely be going through IRIDIUM. But the broadband companies are Starlink and OneWeb. Starlink is a division of SpaceX, Elon Musk's company, and they've already launched, believe it or not, 1,800 satellites, in round numbers, 1,800 satellites, and their plan is to ultimately launch 12,000 satellites, all with the purpose of providing broadband to fixed stations at a building or at another fixed location. OneWeb, same idea, broadband to fixed stations. In this case, OneWeb has already launched 218 satellites, and their plan is to go to a total of 648 when their full constellation is up there. Just wanted to stop for a minute and talk to you a little bit about orbital inclinations. This will be important when you hear from Jens. I've already talked about a polar orbit, like the IRIDIUM orbit. That's one that goes from over the South Pole to over the North Pole and back again. And this is a picture of the Earth looking head on at the Earth. And you see the equator here as a horizontal line, and you see the polar orbit as a vertical line. Now that vertical line that represents the polar orbit actually extends beyond the edges of the Earth. And that's because when a satellite is over the North Pole, it's above the North Pole. So it's above the edge of the Earth, and then the same with the South Pole. What we mean by orbital inclination is the angle between the equator and the orbit. So you can see that in this picture, the angle between the equator and the polar orbit is 90 degrees. And to be actually technically correct about that, we would say that the angle between the equatorial plane and the orbital plane is 90 degrees, but stated more simply, it's just the angle between those two lines. We're showing two other kinds of orbits here. The one that looks like it's at about 45 degrees is actually 53 degrees. And so that one has an orbital inclination of 53 degrees. And then the one in between has an inclination of 70 degrees. And, you know, we didn't pick these numbers arbitrarily. These actually represent the orbital inclinations that are being used by OneWeb and by Starlink. To be a little more specific, OneWeb is using an orbit at 1,200 kilometers, about 700 miles up, and they are in polar orbit, an orbit that is, in round numbers, 90 degrees. So that one is pretty easy to understand. If you just think about the IRIDIUM animation that I showed you, that's the kind of orbit that OneWeb is using, although OneWeb will ultimately have many more satellites up there than IRIDIUM does. Starlink is a little more complicated. Starlink is using orbits at altitudes between 540 and 570 kilometers. The numbers are actually 540, 550, 560, and 570, all about 300 miles up. And Starlink will ultimately use all three orbital inclinations, 53, 70, and 90 degrees, although the satellites that they have in the air right now are all at 550 kilometers and 53 degrees inclination. Here's what the Starlink constellation will look like when all of its satellites are up there. It looks pretty dense, looks like a swarm of bees. And that actually emphasizes the density that you'll get with having many satellites, and especially at such a low altitude as 550 kilometers. But in terms of the constellation that Starlink has in the air right now, it looks like this. This is the 53-degree inclination orbit. And as Alaskans, the first thing you'll notice probably is that it doesn't cover us. It only comes north. The satellites only come north to about 53 degrees latitude, which means if you stretch that a little bit, because you could point your beam a little farther north, it might get up to 53 or 56 degrees latitude, but definitely not far enough north to cover the main part of Alaska. So that's what the Starlink constellation looks right now. And as I'll describe in a minute, they are actually starting to provide service by providing their customers with a little dish antenna that looks like this. That's a 1.2 meter or a 3.5 foot dish that they send you, and you mount it on your roof and plug it in, and they say, away you go. They say it'll work. Quite a few months ago, Starlink announced a beta or a trial project where they were beginning to serve some northern states, northern tier states, as they're called. That would be states like Minnesota and Michigan, but not us. And just on a trial basis, they started talking about 100 megabit per service, 100 megabit per seconds uplink and downlink, although that speed actually turns out to be kind of variable, probably depending on traffic levels. People are actually experiencing, in a few cases, faster speeds, but many people are reporting speeds down more in the tens of megabits, maybe 30 megabits, 40 megabits, something like that. In their pricing plan, they offer unlimited data, so there are no data caps. And Starlink is marketing that service direct to the consumer. In other words, if you want to order service from them, you just do it on the internet. They ship you the terminal, in other words, the antenna and the electronics, and you install those yourself and then plug it in. And they say, I don't have experience with this, but they say it's plug and play, just plug everything in and away you go. So that is the Starlink trial. Then recently they announced that they were extending that. A few months ago, they announced that they were extending that to more countries, including some of the ones that are listed here. And they also announced, and this is the part that you'll find interesting, worldwide service this month in September 2021. Well, I'm not sure that they'll meet that, but I think that the thing that's kind of obvious from the picture I showed you of their constellation is they're certainly not providing worldwide service because they're not serving us. Those satellites are capable of, and those orbits are capable of serving mid-latitudes and low latitudes, but not the higher latitudes. So I guess worldwide in this case means something like where most of the world's population lives, which would be, in that range where they have coverage. Starlink, and this is the one that everyone around here is wondering about, is when will they provide Alaska service? And that will be, they say, sometime next year in 2022. I guess it's obvious they'll need to get some satellites up there in higher inclination, and they are planning some launches at 70 degrees inclination. So I think that's when it'll be possible for them to start to serve Alaska. Here's a picture of the OneWeb constellation when all 648 satellites are up. It doesn't look as dense for a couple of reasons. One is because there are not as many satellites, but also when they're in higher orbit, there's more room in that shell up there at a higher altitude. And so that's another reason that their constellation will not be quite as densely packed. So they have 218 satellites flying right now. At least that's the latest information I have. It actually changes for both of these companies. The information changes very quickly, so it's a little bit hard to keep up, but I've given you the latest numbers that I have. And as far as their plan to provide service, unlike Starlink, OneWeb now says that they're marketing to enterprise customers. That would be large customers like good-sized companies and government agencies. And it appears that they will be marketing to individual customers like us, possibly through resellers. There's a project going on in Akiak down on the Kuskokwim River that you may have read about in the news. And that is at least an early indication that OneWeb may be marketing through enterprise customers. And if there's anyone on the call here who has more information about that, we'd be more than happy to learn about it, but that's pretty much what we know at this point. OneWeb has announced that they'll provide service in the Arctic region, which I guess includes us, in late 2021. So that's coming up very soon, and global service by the end of 2022. So that's some information, mostly from public information about what Starlink and OneWeb are planning. There are, I don't know if controversies might be too strong a word, but there are some issues that some folks are concerned about. One is light pollution. If an astronomer looks through an optical telescope at trying to see an object far away in space, he will sometimes be concerned about bright objects like, for example, Starlink spacecraft on their way to full orbit, because the solar panels may be reflecting light off the sun and down to the Earth, and that may be disrupting the work of astronomers using optical telescopes. Other people, not necessarily astronomers, may be concerned about that, but they may not like those extra objects in the sky. Another issue is space junk. If you saw the movie Gravity, you know about this one. With so many objects flying around up there, it seems pretty likely that at some point there will be some collisions. In fact, back to IRIDIUM, IRIDIUM has already lost one spacecraft due to a collision. But then in sort of the Gravity scenario, if a collision throws off multiple fragments and those fragments then cause other collisions, you could get a chain reaction, and that definitely is a pretty big concern. And then another issue, this may not be a complete list of all the issues, but these are some of them. Another issue is radio interference, and that is that the possibility of LEO satellites interfering with GEO satellites and or LEO satellites interfering with each other. So we're going to talk a little bit more about the radio interference issue. Specifically, in this presentation, we're going to talk about interference between LEO satellites and GEOs. Now, there are two spectrum regulators that are involved here. One is the US Federal Communications Commission, and the other on the international level, the United Nations International Telecommunications Union. Both of these have announced similar requirements. Well, it's not recent, the requirements have been there for a while, that LEO systems may not cause harmful interference to GEO systems. And in the radio world, it's kind of traditional that that legacy systems are protected. Systems that have been or already are in place will be protected from newer systems. If they're sharing spectrums, then the newer systems need to protect the legacy systems. In this case, the GEOs are the legacy systems, and the LEOs are the new guys on the block. So the LEOs are obligated to protect the GEOs from harmful interference. And that situation is particularly important because they're sharing some of the same pieces of spectrum, specifically the Ku, Ka, and V bands. The one that is of the most immediate concern is the Ku band. For radio engineers, that means for geosatellites, that means an uplink at 14 gigahertz and a downlink at 12 gigahertz. Because there are lots of geosatellites that are using that spectrum, and some of the new LEO systems are planning to use that same band to provide a link to their customers on the ground. So spectrum sharing in that band is, maybe a more immediate problem than some of the others. So just to talk a little bit more about interference, a LEO causing interference to a GEO, it's illustrated in this picture where you see a GEO Earth station communicating with a GEO satellite far away in high orbit. And then there's a LEO satellite, which is in much lower orbit, represented by the red circle. And that, as you can see, as that LEO satellite goes through its orbit, it may at some point be within the field of view of the GEO Earth station. So if the LEO satellite, for example, is transmitting on the same channel where the GEO Earth station is receiving, this would be one example of interference, then that would be a problem. That could cause harmful interference. And also, it's not just a question of this one LEO satellite. There will be many LEO satellites in orbit, and there will also be many GEO Earth stations that are potentially susceptible to interference. So that's the kind of interference that is that the regulators have said, can't happen, should not happen. So what the situation that is illustrated here is what's come to be called an inline event. In other words, if the LEO satellite is in the field of view of that GEO Earth station, in other words, it's in line with the GEO Earth station and the GEO satellite, then there is at least the potential to cause interference. It's not saying it will cause interference, but it might cause interference unless you do something to prevent that. So what are the things that you could do? Just kind of thinking from just starting from scratch, if you were in line, if you were LEO and you're in line, you could power down, you could turn off your transmitter. In order to do that, you would have to know where the GEO Earth station is, you would have to know where the GEO satellite is, and you could power down in that case. You could also change frequency if you knew what frequency those two, the GEOs, were using. Or another option would be to use beam steering to just steer your beam away from the Earth, from any Earth stations on the ground that, you know, that might receive interference. Well, the one that we like and the one that we've become interested in is beam steering. And in fact, Jens is going to talk about a method to use beam steering that does not require the LEO operators to know the positions of the individual GEO satellites, the positions of the individual GEO Earth stations. And that's a pretty big deal, because knowing the positions of the GEO Earth stations would be a pretty tall order, given the thousands and, you know, many, many thousands of them, including Earth stations that just receive just their dish TV or something like that. So the reason we like this method is because it doesn't require knowledge of any of those things to protect the GEOs. And it also doesn't require knowledge of the particular frequencies that are being used. So that's pretty much our goal in looking at this work. Full disclosure, we, you know, the LEOs have not told us. We don't know exactly what they're doing to prevent this. We know they're required to do it, but if they asked us, this is Jens is going to explain. If they asked us, this is what we would tell them. And so now I'll turn it over to Jens. Jens, take it away.
Thank you, Alex. Can you hear me okay?
Yep, go ahead.
Good. As Alex mentioned earlier, both the FCC and the ITU require the LEOs to protect the GEOs. In other words, a LEO cannot interfere with the signal from the GEO. So in my first slide, okay, there we go. What I'm showing is actually the absolute worst case scenario, where I have a LEO projecting its antenna beam exactly in the line of sight between a GEO and a LEO. So what's the problem with this? Well, you can imagine if there happens to be an Earth station in this projected LEO radiation pattern, as I have it labeled, the LEO is likely to interfere with the GEO. And again, this is exactly what is not permitted. And are there a lot of GEO Earth stations? Well, if you have satellite TV, you have a GEO Earth station. So yeah, there are plenty of them. So the next thing we might want to look at are basically a two-scale depiction of the GEOs and LEOs. And in this case, I'm showing the GEO satellites kind of on a semicircle around the Earth, which is shown there in blue. I'm showing the GEOs as these dark black dots, and I've spaced them every 10 degrees. So if you do the math, and I imagine that they were surrounding the Earth, which they are, that would give you 36 of them. In fact, there's over 400 of them. So a more accurate picture would be, to have one of these dots every degree instead of every 10 degrees. But I think this is going to be good enough to make our point. The Earth, you can see as being, you can see the LEOs orbiting there. I'm using an orbital tilt of 53 degrees in this picture. You can't really tell that from the angle that I'm showing. And I'm also showing kind of a range of LEO satellites, and perhaps the LEO is kind of moving from the north through the equator to the south. So our aim is to actually find where the line of sight between a GEO and any one of these LEOs might project onto the Earth, or if in fact it does project onto the Earth, because it turns out that if your GEO is far enough to the east or west, it won't project onto the Earth. And if your LEO is far enough to the north or south, you also won't get a projection onto the Earth. So what we really have to do is to consider every single combination of LEO and GEO. Here's one example. And do a little bit of basic trig to find out exactly where that point projects onto the surface of the Earth, if in fact it does. So that is basically what this slide is supposed to show you. So initially, I mean, our knowns would be the radius of the Earth, and we'd actually be able to calculate that angle alpha. So what we know is the vector from the center of the Earth to the GEO and the vector from the center of the Earth to the LEO. And that is enough information to calculate everything else, including the final thing that we need to know, which is where exactly does that point project onto the surface of the Earth. So another thing that I kind of showed on the first slide that I want to get into a little bit more is the effects of the antenna beam width. And I'll show that on my next slide here. And so I coded up a circular aperture antenna and calculated its radiation pattern. This would be the power per unit area for I think a 2 wavelength circular aperture antenna. And it just kind of gives you an idea that, you know, even if your antenna is pointing a little bit off of the line of sight, you still have to consider that your beam has a particular width to it. And that beam, you know, if you were to project it on a flat surface, might project as a circle if you're looking straight down. And as you increase the angle of that beam projecting onto that surface, that projection becomes increasingly elliptical. And this is actually a slide that I made years ago when I was working at Bird Polar Research Center, and we were actually looking at the projection of an antenna beam onto the surface of the snow in Greenland. We were trying to reconcile ground-based and satellite-based data. So I thought I could use it for this talk, just to kind of give you an idea of what happens when your beam starts to hit that flat surface at an angle. So our problem is a bit more complicated than that, though, because we have to now project a beam of this form onto a circle, in other words, onto the Earth's surface. And so my next slide, I kind of want to do just one example of a LEO orbit with a geosatellite that would have been to the extreme west. If you can see that small black dot along the orbital path of the LEO, that's my LEO satellite. I don't show the GEO, but what I'm showing is how that antenna beam, which I assume to be 10 degrees in this case, would project onto the surface of the Earth. And you see that that beam is really smeared across the surface. And eventually the right side of the beam you see is truncated, and that's due to the fact that the Earth, the curvature of the Earth blocks part of the beam. So we needed to account for that as well. But that red splotch, beam projection, is actually what we would refer to as the forbidden zone. So if that particular LEO transmits information in that direction, it'll interfere with that respective GEO. And so we might want to do that for a range of different beam widths. I kind of want to show you what happens as the beam width changes. And I'm going to consider more than one GEO now. I'm going to consider that same single LEO in a range of GEOs. And let me just tell you a little bit about where that LEO is. So again, this thing that looks like a straight line tilted an angle of 53 degrees is actually orbiting around the Earth. And we're just kind of looking at this plane from the side. So if you consider that this orbit takes 360 degrees, what I'm showing now is when the orbit is, I think, 60 degrees along its path, starting from the equator. So starting from the equator is 0, it moves 60, it moves around the Earth, and again, it takes 360 degrees, the LEO, to transverse its orbit. So what I'm showing in this figure is the effect of beam width, because that's something else that affects the forbidden zone. So if your LEO happens to have a very sharp beam, it projects a smaller forbidden zone, and that's shown in that first image on the left. And I'm increasing the beam width from 3.3 degree full beam width to 6.6, 10 degrees. What we see is the forbidden zone thickens as the beam width increases. And I haven't shown this because all of my examples that I do, I assume that my LEO is at 1,000 kilometers. So again, it's kind of in between those the two altitudes of the two satellite systems that Alex discussed. But the other thing that would happen as you move further out, that forbidden zone does increase because that projection increases. And likewise, if you move closer in, if you were at 540 kilometers versus 1,000 kilometers, it would actually make those projections, make that forbidden zone smaller. So if you count the number of dots in each of these, you'll find that only 9 of those geostationary satellites intersected the Earth. The other ones went off into space, harmless. But the other thing that I mentioned was that really that these satellites aren't spaced every 10 degrees. They're really less than 1 degree if you included all of them. So that those dots you could almost imagine smearing into some continuous line. You may even be tempted to take a Sharpie and fill it in yourself. So for the next slide, what I want to show is the effect of a single LEO kind of moving from 0 degrees to 20 to 40 to 60, just so we kind of get an idea of how that forbidden zone changes as our satellite moves along its orbit. And you see that at the equator, which is that first panel on the upper left there, it's very symmetric, and I guess kind of what you would expect. And as the satellite moves further north to the final panel, which would be the lower right, you see that those antenna beams get increasingly skewed to the north. So again, that region seems rather large, that forbidden zone if you're in the north there. So we might also want to consider what happens in the southern hemisphere, because I know Alex spends a lot of time in the southern hemisphere. So no surprises here. It's essentially a mirror image of what happens in the a mirror flipped image. So it's kind of exactly what you may expect if you think about it a little bit. And I'm showing this just for completeness because I'm not going to show the southern hemisphere anymore because it doesn't really add anything additional. So what I might want to consider next are some different orbital inclinations. So everything I've shown you so far is 53 degrees. So what I want to show you just kind of quickly, I'll go through these last two slides. They won't take too long, just to kind of show you how things change at 70 degrees and 90 degrees. So my next slide, we can just look at the same situation, except at 70 degrees. And here, I guess the interesting thing that happens as our LEO satellite moves from 0, 20 degrees, 40 degrees, and finally 60 degrees along its orbit, what you see is that even at 60 degrees, the LEO is so far north that there isn't any interference from any of the GEO satellites. So in other words, there isn't any location where the LEO GEO line of sight projects onto the surface of the Earth. And the same thing occurs at 90 degrees, which I'll show is my second. I have a couple more slides after this, but in the same situation as my LEO moves from 0, 20, 40, 60 degrees into its orbit, you know, at 60 degrees, no interference, not surprising. And of course, when I have these polar orbits, the projections for a given, you know, rotation through my orbit become further north, which you may have noticed. So my last two slides are kind of a fun, you know, what if type of scenario. So, but the first slide I showed you, I basically had the LEO rotated so that its antenna beam was pointing directly along the line of sight between the LEO and the GEO. And for this one, just for fun, what I want to do is assume that my LEOs are always pointing straight down. And what that means is that my LEOs are always pointing towards the center of the Earth. And so what I can do now is define an angle delta that measures the angle between that downward look and my line of sight. And if you remember that for a given LEO, I would have all these GEOs that I need to concern myself with. So all these GEOs are going to have a different line of sight for a particular LEO. And so what I notice in this figure is that as long as that angle delta is greater than a half a beam width of my LEO, then I'm fine. I'm not going to get any interference. So what I want to do in my final slide is basically show you a bunch of different deltas for a range of LEO orbital inclinations, orbital angles. So I'll do my best to kind of explain what I have here. So what I'm doing is considering a range of LEO satellites from minus 30 degrees to plus 30 degrees along its orbital path. So it would go from minus 30, pass through equator, and go to plus 30. And what I want to do in each of these cases is measure that angle delta for each of the GEO satellites that are within its view. And so that's kind of what I've done with these curves. And what you've noticed is that they generally go down, they hit a minimum, and then they go back up. And that minimum occurs when that particular LEO is the closest to that particular GEO. That's when that angle delta that I showed you is as small as it can be. And it turns out that if you're at a 30 degree, if you're 30 degrees into your LEO orbit, the smallest your delta ever gets is 18 degrees. And if you have a 10 degree full beam width, you are never in danger of getting any interference. And what the whole purpose of these curves here is to really show you that the only time you would ever be in trouble if you were a LEO pointing straight down is when you're passing through the equator, when you're within about plus or minus 7.5 degrees of the equator. That's when you need to start thinking about steering your beam in a different direction. And I am just going to end it here and throw it back to you, Alex, if that's okay.
Okay, great. Thanks, Jens.
You're
And
welcome.
I will just finish up by mentioning again why we're investigating this particular beam steering approach to avoid interference. And the advantages of it are that it does not require that the LEO operators know the positions of individual geosatellites. In fact, this would protect all the geosatellites that are anywhere along the arc. The LEO operator does not need to know the positions of the individual GEO Earth stations on the ground, and the operator does not need to know exactly which frequencies are being used, because all the positions on the ground are protected, all the geosatellites in orbital arc are protected, and all the frequencies are protected by using this beam steering approach. What is the approach? It's simply to avoid those forbidden zones, avoid those red zones that Jens had on his slides. And of course, you noticed from Jens's presentation that those forbidden zones kind of move across the Earth as the LEO satellite moves. When the LEO satellite is in the northern hemisphere, then the forbidden zone tends to be a little bit north of the satellite's latitude, and then in the southern hemisphere, a little bit south of the LEO satellite's latitude. So just steer that beam at least a little bit north or a little bit south, and we think that interference can be avoided that way. So that's what we have in mind. As I said, we're not working with any of the LEO broadband companies. This is just our own work, and we'd be interested at this point in your questions and comments. Thank you.
Yes, I would like to thank you, Professor Hills and Professor Monk, for the great presentation. I would also like to thank those of you who joined us online today. Our next seminar will be next week on the 17th. And once again, the password is broadband, all lowercase. You all have a great weekend and stay safe. Thank you.